All right, let's go ahead and look at these problems from the mini quiz that we had on units 1 through 3. A student has a 100 milliliter sample of 0.4 molarity copper sulfate and is asked to make 100 milliliters of 0.15 molarity copper sulfate for a spectrophotometry experiment. The following laboratory equipment is available for preparing the solution, and you have the following items. A. Calculate the volume of 0.4 molarity copper sulfate required for the preparation. So first let's look at the molarity equation here that we have. If you rearrange this, molarity times liters is equal to moles. This is just a simple dilution problem. We want 100 milliliters of 0.15 molarity. We have a stock solution that is 0.4 molarities, and we only have 100 milliliters, but that doesn't mean we have to use all 100 milliliters of it. So we're going to dilute some of the 0.4 molarity to get it down to only 0.15 molarity. So that's what we're going to try to dilute, and that's what we're trying to find. How much of that 0.4 do we need? So if you can imagine, we're not going to be taking out any moles or adding any moles when we found that value, which happens to be, here's the punchline, 37.5 milliliters. The same amount of moles that are in that 37.5 milliliters is the same amount of moles that we'll have once we've diluted it up to 100 milliliters. So you can see that the molarity times the volume of the original sample is going to equal the molarity times the volume of the second sample, or the new sample. So that's why this dilution equation works. M1V1 is equal to M2V2. The original molarity is 0.4, and we're going to try to solve for V1. The M2V2 is the values that we know we want to have, 0.15 molarity and 100 milliliters. When you do the calculation, you've got 37.5 milliliters. B. Briefly describe the essential steps to most accurately prepare the 0.15 molarity copper sulfate from the 0.4 molarity copper sulfate using the equipment listed above. So here's the interesting thing. Graduated cylinders are accurate. Of course, they're more accurate than a beaker or a flask, but they are actually not the most accurate piece of glassware. Either a burette or a pipette is even more accurate. So that's what you're first going to do, is measure out the 37.5 milliliters of 0.4 molarity copper sulfate, our stock solution, using either a burette or a pipette. Then you're going to take a 100 milliliter volumetric flask. The key word here is volumetric flask. We are not going to use a beaker. The line of 100 milliliters on a beaker is nowhere near accurate. You could add like 10 milliliters to it and it'll still look like it's at the 100 milliliters because it's so wide, and there's very few other markings between the 100 and the next mark of like 150 or down below 50. So we take a piece of glassware like this. It will label, it's kind of blurry here, but it's going to label somewhere at the bottom exactly how much it can measure, either 100 or 250, sometimes the smallest is only 25 milliliters, and there's only one marking. It's usually some sort of etched line on the neck of the glassware. You can only measure the value that this flask states. So you're going to pour in the 37.5 milliliters up into here, and it's going to fill, a small amount here, maybe a third. Roughly around here will be your 37 milliliters. Then you slowly add in the water until the line is right on the etched line, the meniscus. Remember, you want to measure the bottom of the meniscus. You don't necessarily need to state the concept of the meniscus, but here would be a good answer for step 2. Add the 37.5 milliliters to a 100 milliliter volumetric flask. Then add distilled water to the mark on the flask. All right, the student plans to conduct a spectrophotometric analysis to determine the concentration of copper 2+ aqueous in a solution. The solution has a small amount of cobalt nitrate present as a contaminant. The student is given the diagram left, which shows the absorbance curves for aqueous solutions of cobalt and copper. So this graph is showing us that when the wavelength is roughly around these values here, we're going to actually get to absorb some of the cobalt and it's going to show up. And we don't want to do that. We want to just look at the copper ions. From part C here, the spectrophotometer available to the student has a wavelength of between 400 nanometers to 700 nanometers. What wavelength should the student use to minimize the interference from the presence of the cobalt? So we'd want pretty much the highest one from that available list, because of the graph, it's showing there's very little absorbance of cobalt is going to show up if we use a wavelength of 700. The grade rubric said anything between 650 and 700 is acceptable. Question 2. Using principles of atomic structure, explain why the atomic radius of krypton is less than the ionic radius of selenium 2-. Well, that's because krypton and selenium have the same number of electrons, but krypton has 2 more protons. Thus, the valence electrons in krypton experience a stronger attractive force and are on average closer to the nucleus. Think about it. If they have the same number of electrons, which happens to be 36 electrons each, that means they each have 4 full shells of electrons. So if you kind of want to imagine the Bohr model where you've got your first shell, second shell, third shell, fourth shell, for both of them, that fourth shell should be roughly the same distance from the nucleus, except for the fact that krypton has 2 more protons at the very center. So we've got like a higher, 36 protons. And here we've got a higher attractive force at the center. Maybe you can think of it as a stronger magnet at the center, pulling in all of those shells a little bit closer to the nucleus than selenium can, because selenium only has 34 protons. All right, part B. Photoelectron spectroscopy data for the 1s sublevel of sulfur and the 1s sublevel of selenium are represented below. If you look at the periodic table, you can see that they are in the same column, group 6, both of these, sulfur and selenium. In terms of Coulomb's law, there's your key you need to mention somewhere in your answer, according to Coulomb's law, ... So in terms of Coulomb's law and atomic structure, explain why the peak for selenium is positioned so far to the left of the peak for sulfur. So we're looking at the 1s electrons, which if you zoom into the Bohr model again here, we are looking at the very first shell. These are the 1s electrons. There's only 2 electrons in that very first shell. So according to the graph, it's showing that for selenium, the binding energy is so much greater than it is for sulfur. Well, here's the answer. The attraction between the 1s electrons and the nucleus in selenium is, I don't think I wrote that. I think I missed out a couple of words there. In selenium is much greater than in sulfur because the selenium nucleus has 34 protons and the sulfur nucleus only has 16 protons. So according to Coulomb's law, the attractive force is stronger when the magnitude of the charge of the particles is greater. Remember, Coulomb's law is something like this. You've got force is equal to charge over distance. Consequently, the 1s electrons in selenium are more strongly attracted to the nucleus and more tightly bound than those in sulfur. So even the distance is smaller. So if we're multiplying for selenium a greater charge and then a smaller distance, that's making the force of attraction much greater, which is why the binding energy for selenium is so much greater than the binding energy for sulfur when we're comparing their 1s electrons. All right, so here's some Lewis structures, and we need to talk about formal charge. But first, the question says 3 compounds that contain elements from group 16, these 3 compounds here. Possible Lewis electron dot diagrams for the compounds are shown below. All right, so part C says which structure, A, B, or C, minimizes the formal charge for each atom in SeO2F2, and justify your choice. So let's review formal charge. The formal charge has nothing to do with the overall charge on the particle, on the molecule. If the overall molecule actually had a charge, like if we were drawing the Lewis structure for nitrate, NO3-, then all of the formal charge added up on all of those elements should equal -1. But since we are talking about neutral compounds here, A, B, and C are neutral, then the overall for the formal charge should be 0, but we don't really care about the overall charge for right now. When we're looking at the formal charges of each element, we're wanting to minimize each element's formal charge. So formal charge is calculated by taking the number of valence electrons the atom has according to the periodic table, and then subtracting the electrons we've placed on the structure or that we're looking at on the structure. Now, normally, let's just look at this structure here. When we're counting an octet, say let's count the octet for oxygen, we've got 2, 4, 6, 8. So this oxygen has 8 valence electrons shared around it, and the selenium has 2, 4, 6, 8, 10, 12. So selenium has more than an octet, which is okay for selenium. But let's look at fluorine. We've got 2, 4, 6, 8. So when we're counting octets, we're counting each bond as 2 electrons because technically we've got an electron from fluorine, an electron from selenium in the bond. In the double bond, we've got 2 electrons from oxygen and 2 electrons from selenium. So that's why we count it as 2 when we're counting the shared electrons. But right now, when we're counting the electrons in the structure, we're just counting the electrons that are supposed to be on oxygen. So we would count the bonds as 1, 2, 3, 4, 5, 6. So this oxygen has 6 electrons placed around it. So let's go count each of them. For A, selenium is supposed to have 6 if you look at the periodic table, and it has only 4 right around here. 1, 2, 3, 4. So 6 minus 4 is a 2, positive. So we've got a 2 plus formal charge on selenium. Each of the oxygens are supposed to have 6 valence electrons according to the periodic table, but we've placed 7 around each of them. 1, 2, 3, 4, 5, 6, 7. So each oxygen has a -1 formal charge. The fluorines are supposed to have 7 valence electrons, and we've placed 7. 1, 2, 3, 4, 5, 6, 7. So that means each of the fluorines have a 0 formal charge. So we've got a lot of formal charges going on in this structure. 3 of the atoms have a formal charge. Yes, overall it adds up to 0, but we don't care about that in this moment. Let's look at B. Oxygen is supposed to have 6, and it has 6. So each oxygen has 6 valence, a 0 formal charge. The fluorines are supposed to have 7, and they each have 7 here. So they are each a 0 formal charge as well. Selenium is supposed to be 6, and it has 1, 2, 3, 4, 5, 6. So selenium is also 0. So B is the answer for this, but let's go ahead and count structure C. This oxygen is a -1 because it is supposed to have 6 and it has 7 right here. Each of the fluorines are 0. They're supposed to have 7. They have 7. The oxygen on the bottom has a 0 formal charge, and then this selenium is 1, 2, 3, 4, 5, so it has a +1. So you can see that the answer is structure B because it is the only structure where all atoms have a formal charge of 0, and that is how we have minimized the formal charge. Part D here. A student proposes that the energy of the Se to O bond in the structure in diagram D is less than that of the Se to O bond in the structure in diagram A. Do you agree or disagree with the student's claim? Justify your answer. So here's a tip as far as this test taking. When the question is asking you something like this, whether it's true, false, disagree, or agree, or increase, decrease, or something like that, state that answer first. And even like I put here, disagree, period. So now the reader or the grader kind of knows that you're, or at least hoping that your justification is going to support that correctly. Whereas if you were to put the incorrect part here, it's kind of easy to see you've lost the entire point. Okay, so disagree. The Se to O bond in D, structure D here, is a double bond, which has a greater energy compared to the Se to O in A, which is a single bond. In other words, you could say that it requires more energy to break the double bond between selenium and oxygen than a single bond between selenium and oxygen. All right, question E. The dipole moment of the SeOF2 molecule in diagram D is non-zero. Identify its molecular geometry and explain how its geometry and the polarity of its bonds results in a non-zero dipole moment. So the molecular geometry is trigonal pyramid. You just need to have a bunch of those molecular and electron geometries memorized. The molecule is asymmetric because of the lone pair of the electrons on the central atom. Let's look at this structure here. Therefore, it is impossible for all of the individual bond dipoles to cancel completely. There are 4 electron domains around selenium. 1, 2, 3, 4. The lone pair counts as a electron domain. So its electron geometry would be considered tetrahedral. But because it asks for the molecular geometry, you're going to look at what the molecule name, how it changes when you've replaced one of those attached atoms with a lone pair here. Instead of having a 4th attached atom on this 4th side, that's why it's called trigonal pyramid. And in order to be symmetrical, every single thing, or I should say domain around the central atom needs to be identical. And so even if all 3 of these attached atoms were the same atom with the same type of bond, The lone pair right there makes it so that all 4 of the domains around the central atom are not identical. Therefore, this is a polar molecule because it's asymmetric. And that's why the bond dipoles don't cancel completely. Part F. Boiling point of SeOF2 is less than the boiling point of SeOCl2. So we're going to look at diagrams D and E. Identify the types of intermolecular forces that the 2 substances have in common. So if you look at both of these structures here, you can see that they both are asymmetric, therefore they're both polar. They both experience dipole-dipole interactions and London dispersion forces. Remember that London dispersion forces is an attractive intermolecular force that every single molecule experiences. Non-polar molecules only get to experience the LDF or London dispersion force type of intermolecular force. However, all molecules experience LDF. And since both these molecules are polar, they both also experience dipole-dipole. So that's why the answer is that way. Explain the difference in boiling points based on types and relative strengths of intermolecular forces. This is specifically relating to part F. So SeOF2, it's telling us, actually in the problem here, that SeOF2 has the lower boiling point. So it wants us to use our answer in part F to explain why it is lower, even though they both experience the same type of intermolecular forces. So SeOF2 has fewer electrons, thus a smaller electron cloud, which is less polarizable. Therefore, the IMFs between SeOF2 are weaker than between the SeOCl2, resulting in a lower boiling point for the SeOF2. When you're comparing molecules that are experiencing the same intermolecular forces, whether it's 1 or 2 or 3 different types of IMFs, if they're all the same, you're going to look at how many electrons each of the molecules have. The one that has the more electrons is going to be more polarizable and therefore experience stronger forces and will have the higher boiling or melting point. All right, last problem. We have to balance this equation. So I like writing out all of the elements that we have listed right underneath the arrow. And then I've counted on the left side, we've got 1 selenium, 2 oxygens, 2 fluorines, 1 sodium, 1 hydrogen, and then on the right side I've counted them up as well. So far the seleniums are balanced. We're not going to try to balance oxygen because it appears in 2 molecules on each side. Therefore, just about any coefficient we change is going to change our oxygen. So there's no point in trying to balance out the oxygens first because they're just going to get unbalanced later on. So let's look at the fluorine. In order to balance the fluorines, we're going to add a 2 coefficient here so that now we've got 2 fluorines. And now we have a total of 4 sodiums, 2 here and 2 here on the right-hand side. So then going over to the left-hand side, let's add a 4 to this coefficient. So now we have 4 sodiums. We now have a total of, let's look at our oxygens, 1 here plus 4 more. So we've got a total of 5 oxygens. And then for hydrogen, we have a total of 4 hydrogens. So it looks like we just need to change the water coefficient to 2. So now we have a total of 4 hydrogens. We've got 2 oxygens here plus 3 more. That makes 5 oxygens. So then our coefficients, we need to put them over here. A 1, a 4, a 1, a 2, and a 2. Notice that each of the coefficients must be at least 1. You cannot have a 0 coefficient, otherwise then that means that molecule isn't actually part of the chemical reaction. So if the molecule is listed in the chemical reaction as either a reactant or a product, that means you know you have at least 1 of it. So the A and the C coefficient aren't 0, they are 1 for that reason.